In this brief video, we're going to show you how to find the elasticity of demand when the demand curve is an exponential function. It's an equation that looks like this. Quantity demanded is equal to a positive constant A times price raised to the power alpha. And because this is a demand curve, we're going to have alpha less than 0. That will make sure the demand curve is negatively sloped. So let me go over here and show you what this demand curve looks like. It's a variation on a parabola. We put price here and quantity here, and the demand curve will look something like this. It gets flatter and flatter the higher the quantity and the lower the price. So what's the elasticity of demand in this case? Well, we again know that elasticity of demand is the change in quantity demanded per unit change in price times P over Q. What is it in this case if we do the actual calculation? Well, first we can find dQ dP, and that's going to be alpha times A times P raised to the alpha minus 1 power. And we can attempt to simplify that a little bit by recognizing that that's equal to alpha A P to the alpha P to the minus 1. Now if we compute the elasticity, dQ dP times P over Q, we have alpha A P to the alpha P to the minus 1 times P divided by Q, but Q is A P to the alpha. Now there are many ways to cancel things here. If we look for a different color, we can certainly cancel this P with this P, and we can cancel this P alpha with this P alpha, and this A with this A, so that the result for elasticity is alpha. And this, it turns out, is an exciting universal result. If we have an exponential demand curve and want to compute the elasticity with respect to a variable on the right-hand side, the exponent in the exponential function is the value of elasticity. So let's work out a numerical example just to assure ourselves that this is really going to happen. By the way, you might note why this is important in economics. This is a really simple function to work with, yet it provides the possibility of nonlinearities along different portions of the demand curve without really giving up any degrees of freedom. There are still only 2 parameters in this exponential function, the same way there are 2 parameters in a straight line or linear function, and yet we have a lot more flexibility. And it turns out that this exponential form of the demand function is used in a tremendous amount of empirical work, statistical explanations or estimations of demand curves using real-world data. So let's get back to our example. This is an example, the kind of example with exponential functions that are going to come back again and again in the course. We'll have utility functions that are exponential. We'll have production functions that are exponential, in addition to demand functions that are exponential. So here's an exponential function with real numbers instead of A's and alphas. Quantity demanded is 30 times P raised to the minus 0.5 power. And the question is, what's the elasticity of demand? Well, first thing we have to compute is dQ dP. And that's going to be minus, let me scrape this out here. That's going to be equal to minus 15 times p raised to the minus 1.5 power. And if you operate with this a little bit, probably the easiest thing to do is to minus 15 p to the minus 1 p to the minus 0.5. And now we have to multiply that times p over q. So we'll have dq dp times p over q is equal to minus 15 p to the minus 1 p to the minus 0.5 times p over q, and that simplifies to be 15 by canceling the p's, 15 p to the minus 0.5 over q, which is 30p to the minus 0.5, 30p to the minus 0.5. So the answer, conveniently enough, comes out to be 15 over 30, which is 0.5. And that is no accident that that happens to be equal to the exponent in the original demand function. That turns out to be the same 0.5. So if I give you the equation of a demand curve that's of the exponential type and ask you what the elasticity of demand is, you will know by looking, without doing the computation, that the elasticity is going to be the exponent. And this is a proposition that's going to come back again and again as we go through the course. So good luck with it, and we hope you understand it.